In this segment, we're going to look at the count min filter, and this count min filter is used to detect heavy hitters. And so, a typical example application would be in a network where you want to monitor traffic, and you have packets of arriving from various sources and reaching towards various destinations. And these heavy hitters are those sort of what people call elephant flows. They're talking about those source destination pairs that are taking up a lot of the bandwidth. So just by quickly observing the traffic flowing through the network, we need to be able to identify those source destination pairs, for example, that are most frequently using a particular router, that particular router. So in these contexts, we can use the count min filter. So let's be a little bit more precise about the data model, the data stream model. Our items in the data stream arrive one after another. We call them x1, x2, and so on up to some xt, and they follow what is called the cache register model. So each element in the data stream, say xt, comprises two items, two components to it. There is the item IT, so this could be, for example, the source destination pair that we are interested that this particular packet is connecting between, and CT is a positive count. It's an increment value. Perhaps this could represent the number of bytes that are being sent from this particular source to this the destination, or something like that. But keep in mind, the same item can get repeated. So x1, xt, t plus 200, all of them could be the same item. So if you were to look at it from the perspective of the network example, the same source destination pair can send some number of some amount of data at one point in time, a little bit later some more amount of data, and so on and so forth. And this cache register model is going to update the total count, and the total count of a particular item I is denoted by count I comma t, and this count is given by this summation. So we sum over all time t, and we look for those items IT that match the item I that we are interested in counting, and when they do match, we add up their count. So that's the count of a particular item I from time period time 1 all the way to time capital T. And we define a heavy hitter with respect to a threshold Q, and it's simply any item whose total count is at least Q. So that's a very natural definition for a heavy hitter, and that will help us to formally understand and approach this problem. So here's the output that is required. Now keep in mind that this problem, the heavy hitter problem, is going to come with three parameters apart from the stream. It's going to come with the threshold Q that divides heavy hitters from non-heavy hitters. Then there is the error parameter epsilon, and the confidence parameter delta. Okay. Now the output will be a set of items such that every heavy hitter that has a count more than the threshold Q must be included. This is a deterministic requirement, and but some items that are not heavy hitters may also be included. So in other words, there can be some false positives, but an item with a count that is significantly far from the threshold, so that's whose count is less than q minus epsilon times uppercase q, is included with probability at most delta. So it doesn't get it should be hard for an item with a small count of q minus epsilon q to be included in the set of items that we output. And here, what is this uppercase q? It's the total count over all items, not just that particular item, but over all items. Okay. And here's something that you need to notice. If there's an item with total count between q minus epsilon q and q, then they don't care. So if they get included, that's fine. If they don't get included, that's also fine. We don't particularly care about whether they get included or not. The solution to this problem is via the count min filter, and this, as you can imagine, uses hashing, but in a very interesting way. We're going to maintain some number of counters. We're going to maintain, in particular, we're going to maintain m counters, but we're going to lay out the counters in this sort of two-dimensional array form. So there are going to be k rows and m over k columns. So keep in mind that it's starting at 0 here. And each row corresponds to a hash function. So this row A corresponds to hash function HA. Okay. Each of these hash functions is drawn uniformly at random from a large 2 universal family of hash functions. Now, given an item, given the arrival of some IT, comma CT, IT is the item, CT will be the count of that particular arrival of that item IT. Here's what we do. We hash the item into we use each of the hash functions and hash it. And let's say now we use HA and it gets hashed into location J. So that's this location over here. Okay. So then we go down row A, because we are currently considering hash function HA. We go down row A up to column J. So that's this location over here. And remember, that's a counter. And we simply increment that counter with CT. Okay. And this is, of course, done for all hash functions. Remember, we have k hash functions, so we do this for all k hash functions. So for each of these hash functions, we go to the we hash the item and then walk down the row corresponding to that item and find the hashed location and increment the counter. And of course, we have to start all the counters at 0. So now let's look at an example just to see how this works. So here's the arrival of a sequence of items and their counts. So now what do? We look at the first item, I1, and find out all the locations that it hashes into. So we are using k different hash functions, and wherever it hashes into in each row, according to that particular the particular hash function, we increment the counter. So for example, since we initialized all the counters to 0, let's say we will make this C1. Okay, and then we process item I2, and let's say I2 hashes into these locations. So let me use a different color. So let's say C2, C2. But remember, it can every once in a while hash into a location that's already being used. So for example, this could be C1, C2 over here. So if that's the case, you go and add C2 to the previously existing quantity, and then we process the third item. And now let's say, for example, just for the argument's sake, let's say I1 is actually equal to I3. So these two are the actually the same item being repeated. So then we'll have to go in and add. So I3 will be hashing into the exact same locations that I1 hashed into, and therefore we have to go in and add these quantities. So here is going to be all in this location. Okay. So this is how the count min filter works. And as you can imagine, how would you find out whether an item is a heavy hitter or not? Let's look at some arbitrary item I. We will now look at the hash locations where I maps to, and look for the smallest counter in those locations. And here's the reason why. For example, let's say that I is actually equal to I1. Then we will be looking at these locations. This location, this location. Notice that because of some overlap in the way the hash function works, some of the counters are going to be large. But if you look at the minimum, and in this case we've only processed very few, so there is more than one minimum. They're all C1 plus C3, and notice therefore that this minimum that we are looking at is going to be at least the count of the item I. It could be a little bit more, especially if once the count min filter table starts to get filled up, there could be more collisions, and therefore there can be more. I mean, the minimum could actually be corrupted with other items because they also hash into that location. But nevertheless, the minimum is going to be a lower bound on the actual count of the item. So just to formalize, let's denote a location or rather the count value of location A, comma J as C A comma J T, and this is the value of the counter at the end of time t. So what we have done is we have processed several items. We have counter values in this table. And remember, we are trying to estimate the total count of each item I comma t to figure out whether it's a heavy hitter or not. And this count is nothing but the summation over the appropriate items in the stream of their count value CTs. So as I just mentioned, just to make it formal, suppose we want to estimate the count I comma t. At the end of time t, we look at all the hash locations for item I, and those are denoted by C A comma J, and we look at their counter values. That's C A comma J of t, and the minimum of all of them is guaranteed to be at least the actual count value of the total count value of that item I at the end of time t. So that's exactly what we explained a little while ago with that example. Now this is just a formal description of the algorithm to estimate the total count. So the key question here is, well, we clearly have intuition that it is an upper bound on the total count, but will it overshoot the total count by too much? That's the question, because if it overshoots, then it's no longer a good estimate. It's okay to overshoot just a little bit, but not too much. Okay, so that's the key question, and our analysis is going to be focused on answering that question. Okay, so now we have discussed how the count min filter works, how each item is processed. You go to the appropriate location within each row and increment the counters. And then after you have processed all the items, if you want to identify the heavy hitters, you just have to look at the hash location of each item that you are interested in and see whether and see all the hash locations and find and spot the minimum, and that minimum is an upper bound on the total count value for that item. And so all items whose minimums are more than the threshold value should be reported as heavy hitters. So that's how the count min filter works. Now we have to analyze and show that the excess, that we didn't overshoot too much. And for that purpose, we're going to define the random variable ZA, and that's equal to the actual counter value at a comma j. And so keep in mind that we're focusing on a particular hash function a. And so this, remember, this will be therefore an upper bound on this count I comma t. So this quantity is going to be a non-negative quantity, and this difference tells you how much we have overshot, and so naturally ZA is what we want to. Okay, so now to get a handle on ZA, we define an indicator random variable xt, and that xt is going to be 1 for all those items whose when hashed with HA lead to the same location J as item I. Okay, remember, so right now we're interested in how much CA comma J of T is overshooting the total count of I comma T. Okay, so this xt equal to 1 whenever the ath hash location matches that of item I. And remember, we are interested in the excess, so this excess should be created by items other than the item I that's of interest. So we need this extra condition to ensure that we're only counting those items that are not I itself. Okay, under this indicator variable, it's clear to see that ZA will be the summation over all time xt, which gives you the indication as to whether that particular item should be counted in ZA or not, times ct. And remember that we are using hash functions, and we are in particular we are using hash functions drawn uniformly at random from a 2 universal family of hash functions. So the probability that a particular item I that's not IT that's not I will have the same location. These two items will have the same hash location with probability at most 1 over the total number of hash locations. But remember that in this table, the number of columns is m over k. So this probability is therefore 1 over m over k, which is nothing but k over m. And this means that the probability with which a particular location, a particular other item will actually hash in the same location, we know that that's at most k over m. So this indicator variable will have the expected value k over m, which means that now we can get a bound on the expectation of ZA. Okay, and if we plug in the values, we're going to get, we can use the linearity of expectation to say that expectation of ZA is equal to t equal to 1 to t count of t times the expectation of xt. Okay. But keep in mind that E of xt is the same for all I, as long as it's not equal to it is not equal to I. So you can take that out, and moreover, notice that the summation overall t ct is nothing but the total summation q over all items and over all time. So this and so we therefore get this bound on the expectation on ZA. Okay. And with expectation, now we are ready to apply Markov's inequality. So now we ask, remember, the whole goal is to ensure that the probability that we will be reporting an item whose reporting a count value that's more than epsilon q over the correct count. That's what we are trying to. That's our bad event. So we capture that bad event in this expression over here. So the this probability of this bad event where ZA exceeds epsilon q now can be written as ZA is greater than or equal to, and I want to write this in terms of the expectation. So I therefore appropriately modify this constant over here. And using Markov's inequality, I can bound this probability to k over epsilon m. But keep in mind, each of the hash functions is chosen independent of each other. So, and what we have is the probability that one of the hash functions will exceed this epsilon q. Now we want we don't care if one of them exceeded that epsilon q. We just wanted to ensure that at least one of them is does not exceed this epsilon q. Okay. So what instead of that event, we instead bound the probability of all of them, the bad situation where all of them exceed epsilon q, and that's given by this event over here. The minimum over all ZAs is still larger than epsilon q, so all of them had to exceed epsilon q. Okay. And because of the independence of the ZAs, we can upper bound this by k over epsilon m. That's for one of the ZAs, the whole raised to the k for all ZAs. And remember, this quantity, this is the probability of the bad event, and we want this the probability of this bad event to be at most delta, and we can achieve that by setting our k to be ln 1 over delta, and to make sure that it's an integer, we take the ceiling, and m equal to roughly ln 1 over delta times e over epsilon. And if we plug these values in, we will get the appropriate delta that we want. So here's the conclusion. So what we have looked at is given a threshold q, error parameter epsilon, and confidence probability 1 minus delta, we can design a count min sketch with m equal to log 1 over delta e over epsilon total number of counters. Of course, we have to arrange this in a two-dimensional array, but this is the total number of counters, and we will also need to use k hash functions, and k here is roughly log 1 over delta. These are hash functions chosen uniformly at random from a two-universal family of hash functions, and these k hash functions should be chosen independent of each other, such that the identified set of heavy hitters at any time t. So we can create a count min sketch that outputs this identified set of heavy hitters at any time t, which is guaranteed to contain all the heavy hitters with respect to q. So it's guaranteed, it's with probability 1 to contain all the heavy hitters. And then for any item I, the probability that that item I whose count value is actually less than q minus epsilon q is also identified and included into the set. So essentially false positive is at most delta. And of course, this is only true as long as this particular item is far from being a heavy hitter. So this is count min sketch, and we Keep in mind that we only needed to use hash functions that are drawn from the two universal family of hash functions, as long as they are mutually independently chosen of each other. And this is a very, very nice data structure. It's very compact. As you can see, the size of the data structure is only a constant. That depends only on delta and epsilon. So it's a very it's become quite a famous sketch. So this is essentially a sketch of the data stream that allows us to identify heavy hitters. So let me end with one final remark. There's one small improvement that we can make, and this improvement is the following. Instead of updating all the hash locations, we can be a bit more conservative about our updates. Normally, we will update all the for a particular item. We will compute the k hash functions, go into those hash locations, and increment all the counters. But the question is, do we need to really increment all the k counters? Remember, the goal here is to ensure that the minimum among all of them is always more than or greater than or equal to the total count of that item. So that is all we require. But if there is some other hash location which has already got a very high value, possibly because of collisions with other hash functions, we don't really need to increment them. So it's best to see this with an example. So let's say that here's our example of a very small count mins filter. So here's what we do. So we are currently in this state over here at time say t minus 1, and we now have to process the arrival of this item I comma 3, and the item I hashes into these locations that are shown shaded. Now clearly now 4 has to be updated to a 7, because remember the count is 3. Okay. Normally we would also update 5 to 8, but what is the point of updating it to 8? We're incrementing the counter for item I, and the minimum is going to be 7. So this and so clearly the total count of item I is 7 or lesser. So making this 8 is of no value at all. Instead, but we should not make it anything less than 7, because that might violate the bound. So all we really need to do is to ensure that all hash locations are no smaller than the new minimum. The new minimum we know is 7. So we just have to ensure that all the hash locations are 7 or more. So the 5 hashes into you go into the location you look at this item, this counter with value 5 in it. Just take it up to 7. Don't have to take it to 8. And this hash location has the counter value 8. It's retained at 8. We don't need to increment that at all. So this gives us slightly better results. But we're going to skip the analysis because that's outside the scope of what we want to talk about. But it's a neat little trick to keep the count min sketch a little bit more sharp. Okay, so that concludes our segment on the count min sketch.